Now, as you might guess, with our expression theta is equal to TL over JG, that formula basically assumed that there was uniform torque, uniform cross-sectional properties as we made our way down the cylinder. Remember that the derivation that we did was based on this angle. It was originally like this, and then it opens up like that. But clearly, if we've got a section that has two different materials, most of the deformation, for example, if this is our silly putty, that's our titanium, is going to be in this particular section. So there is going to be a change in the rotation as we move our way down the length. So just as we had in the case of the axial deformation, we would say that if either the torque, the second polar moment of inertia, or the shear modulus vary in our axial coordinate. Remember, our axial coordinate is this way. If any of those vary in x, then we have to use this. We have to take the torque divided by jg and then integrate that over the length of the bar. So that would be the analog of our integral of p over AE dx. So again, the rotations come from integrating the shear strain, basically. And that's what we've got in a case like this. Now, I would put a soft memorize on this one. In other words, that's not as important. That's probably not going to be as common to have a varying torque, J or G, along the length of the bar as we would for the axial case. But it's good to remember, and it's so close to P over AE that I think it bears memorizing. All right, well, let's go ahead and do an example, and this will be one that'll set us up nicely using both of our memorized formulas. I'm going to try to draw this in 3D. So we're going to have a section that has two segments associated with it. So I'll draw it. I guess I should have drawn that as a solid or a dashed line, but that's okay. Let's go ahead and keep it like so. So there is a section, and then it's going to be attached to a larger diameter section, like so. So we have two circular cylinders, and let's fix this to the wall. Let's go ahead and call this A. We can use that now since the cross-sectional area isn't as important. Let's call this segment B, and then this one C. So we're going to put a torque of 40 inch kips this way. We could say inch kips or kip inches. It doesn't matter. Sometimes we'll say force length, so it would be kip inches. And then we're going to put another one exactly at the junction line, and that's going to be 100 inch kips like so. And these lengths, not exactly drawn to scale. Let's make this one 2 feet. Let's make this one 3 feet. But we already know that we're going to have to convert those to inches because we've used inches in our applied torque. So our unit of length is going to be inches, and then our unit of force is going to be kilopounds or kips. And then let's give some properties from A to B. That is going to be made of brass. That's a relatively soft material. It has a G of 5600 KSI. And this one's hollow. It has an outer diameter of 5 inches. It has an inner diameter of 2.5 inches. B to C is stainless steel, and that is solid, and it has a diameter of 3.5 inches, and its G is a lot bigger. G is 12,500 KSI. Sorry to cram that in there. Okay, so BC is a little bit stiffer, and what we'd like is find the maximum shear stress anywhere. So we would say find tau max. We also want the angle of twist at B, and we want the angle of twist at C. So this is a problem that is going to set us up to do both a stress calculation and the rotation calculation. Now remember when we were doing our axial bar, it's easiest, in my opinion, if we work from the fixed support out. And this is mainly when we want to calculate the rotation. It's not as important if we want to get just the torque, which drives the shear stress, but I think it's a good habit to make. So I'm going to go ahead and draw a side-by-side view of our problem. I'll try to make this a little bit more to scale. There we go. So we've got the 40 going this way, and then we've got the 100 going this way. And again, that 100, you can assume that that acts right at the junction, right at the interface between those two. Now, if we do this, we can easily see the direction of the reaction torque. Since we've got the right-hand rule, I've got the 40 going to the double arrow to the left. I've got the 100 double arrow going to the right. So clearly, to balance this, the reaction is going to be 60 going to the left. And you want to be able to make these statics calculations rapidly and in your head at this point in your career. If you actually have to sit down and draw the arbitrary reaction at the left-hand end and then write the equation of equilibrium for something this simple, I think you can train yourself to be a little bit faster and a little bit quicker. And as you're going to learn, time is money. And so the faster you can be, the more efficient you can be, the better off you're going to be. So that's going to be the reactive torque that we've got. Now, to do the stress calculation, we need the torque inside of each section. So once again, to do the both calculations, we need the internal torques. They are not necessarily the applied. That's very important. So not necessarily the applied. Exclamation point, double underline that. That is a common mistake for students to make. So for example, they would look at this 100 and they would think, oh, well, there's 100 torque inside of that. But that completely ignores the fact that there's another torque inside there. So it's going to be a rare occurrence. It would have to be a very simple problem where the applied torque is the internal torque. So what we're going to do is apply statics. We're going to make a cut here. Let's call that cut number 1. And that'll give us the torque between A and B. Then we're going to make a cut here. That'll be our second one. And that's going to give our torque between B and C. So you have to draw, to get this, I'll put this off to the side, you need a free body diagram. You can't get away with that. That one you don't really want to do in your head necessarily. So we make the cut. I'll draw the squiggle line to infer that there's going to be a cut. There is the torque of 60. Now what we're going to do here, we're going to draw our assumed direction of torque just like we drew the assumed direction of the axial force. So we're going to draw going outward. We're going to draw just like kind of the tension analog. So that is going to be the torque between points A and B. If you wanted to call it the torque in section 1, that'd be fine. If you want to call it T1, any of those are okay. But it's mainly the internal torque, the internal resultant torque that we've got between sections A and B. Now, this statics one is easy. Notice the TAB is equal to 60. In other words, that's the direction that it's going. So the torque is going in that direction using the right-hand rule. And that means the theta is also going to go in that direction. So we'll put parenthetically that the twist of B relative to A is also going this way. And we'll need that a little bit later. So the twist follows the direction of the torque. Let's write that down. Twist follows the T direction. Period. So I'll put a little star like that so we remember that. And since we're here, let's go ahead and draw the next segment as well. So now, again, you draw the entire segment of the first, you make the second cut, and you look at everything that's going on to your left. Again, this is a common mistake for students who are just coming out of statics, that they'll only draw part of the free body diagram. Don't do that. It's the whole thing. So we have 60 going to the left, we have 100 going to the right, and now we draw our torque in section BC, or if you want, call it T2 or T parentheses 2, they're all okay. So now when we do this, notice that in order to balance equilibrium on this, TBC is a negative 40. Or we would say that the internal torque, like that, you could also do it this way, flip the sign and write it this way. So what that means is that the torque, I'll put this parentheses, the twist of C relative to B follows the torque, it follows the twist, and that means it's going to be going this way. It's going to go the opposite direction as the initial. So again, the angle of twist follows the applied torque. So now we've got the value of 40 inside there. Now the good news is, to get the shear stress, we don't really need direction. So good news, tau does not depend on the direction. In other words, we are not going to worry about the sign. There's going to be no sign for tau for these problems. Not for everything. No sign, I'll say, for torsion. We want to be able to know intuitively which way it's going, but we won't say give a plus or minus with it. So let's take a look at AB. We know that the torque, and I'll use some ad hoc designations, the maximum, I think I said torque, the maximum shear stress in segment AB. Where is that going to be? Well, it's hollow, and we know that it's going to be at the outermost radius. So that's going to be the internal torque, so that's going to be our 60, times the outer radius. Well, remember, let me shrink this down. I can do that. I'm having trouble with that. But we've got an outer radius then, an outer diameter of 5. So the outer radius would be 5 divided by 2. So I'm just getting the radius by taking the outer diameter, dividing it by 2. So that's T times rho. I don't think I wrote that down. T times rho divided by J. And the J is going to be pi over 32 times the outer diameter to the 4th minus the inner diameter to the 4th. And we crank that all out, and we got 2.6 KSI. That's the maximum shear stress inside of the section AB, and that brings us up to the end of part B.